Our first one, and this is number 10 on the homework, if you mix 3.76 liters of hydrogen at a specific temperature and specific pressure. So let me just write out my ideal gas law here. So we have a volume, we have a temperature, and we have a pressure of our hydrogen. Plug all those in with the fact that we always know R, and we can find moles of hydrogen. And then you have oxygen also with a volume, a temperature, and a pressure. So we will be able to find moles of oxygen. And then the question is, how many liters of H2O liquid? So I'm going to make this, so this should be H2O gas. It has to be a gas if it's going to be liters at a temperature and pressure. And so we will then figure out which is our limiting reactant and figure out how many moles of product we can form, and then figure out how many liters that is. So I'm going to color code things a little bit here. So for my hydrogen, we have enough information to do the ideal gas law. For our oxygen, we have enough information to do the ideal gas law. And so let's set them up and see what we find. So for hydrogen first, we have, oh, this is nice. We have liters, we have temperature already in Kelvin, and we have atmospheres already. So we're ready straight away to plug in. And I will, since we're doing this twice, use my ideal gas law for in terms of hydrogen. And as you can see, that's a P there. You can see I've solved my ideal gas law for my moles of hydrogen. And I'll plug everything in. I have 1.24 atmospheres. I have 3.76 liters. And this is why color coding things, there are so many numbers in this problem that it, for me, is really helpful to color code things. My R value is the same. And my T, 353 Kelvin. So I can plug all that in. I get 1.24 times 3.76 divided by 0.08206 divided by 353. 0.161 moles of hydrogen. And so I do all my ideal gas laws first, and then I take my moles of hydrogen and set up a picket fence in order to get my moles of H2O, which is my product. For every 2 moles of H2, I get 2 moles of H2O. Oh, sorry. Pretty straightforward math there. 0.161 moles now of H2O. And trying to stay organized here. Now let's do the oxygen in red. I will do the same thing. I will set up an ideal gas law for oxygen. And again, if you don't use these subscripts for the O2s or the H2s, Just make sure you keep track of everything in some way, but the math doesn't change. 2.94 atmospheres of oxygen, 5.12 liters. R is the same. T is 445, and that's Kelvin. And then I can multiply all this out. .94 times 5.12 divided by 0.08206 divided by 0.412 moles of O2. And I can already tell that since I have more moles of oxygen, and I only need 1 mole of oxygen for every 2 moles of H2O, that oxygen is not going to be my limiting reactant. But let's work it out. 0.412 moles of oxygen. Now it's 1 mole of oxygen for every 2 moles of H2O. And now I double that. 0.824. Moles of H2O. Circle back and note that it's always the smaller amount. And I'm not done yet, but at least I've got my moles of H2O. So can be produced. And my last step is for my H2O. It says how many liters. Now I have my moles, I have my temperature, and I have my pressure. The only thing I don't have is my volume. Let me get on screen there. So PV equals nRT. This time I want V. And again, so it doesn't matter mathematically if you put in your H2Os and your H2Os. It doesn't change the math. Just make sure you keep track of everything. I know my moles, which was 0.161. I know my R, and my T is 539 Kelvin, and my P is 2.91 atmospheres. So I'll plug those in down here. R 0.08206 liter atmospheres per mole Kelvin. Temperature 539 Kelvin. And my pressure is 2.91 atm. Now, I haven't done it yet, but I'm going to cancel out my units this time. I do have my atmospheres. I do have my Kelvin. I do have my moles. Moles in the denominator here. Moles in the numerator, or the denominator of the numerator, if you will. The only thing left is liters. My answer will be in liters, which is what it's asking for. 0.161 times 0.08206 times 539 divided by 2.91, 2.45 liters. And so it's like we just did, like we layered 3 different ideal gas laws onto a limiting reactant problem, but the limiting reactant problem still found our smallest number of moles of product. And so it is hopefully the next layer of how to do limiting reactants, and we'll practice them. Any questions?
Yes. So, are you going to be evil and make us find one of the variables in the ideal gas law on top of a limiting reactant problem? Will all the volume, will all the values be presented in this type of equation?
So, I mean, well, let's look at the next problem and see if there are any differences. So, it looks like this problem, so in this problem, I gave you everything in the proper units as well.
Mhm.
But the one thing I could do that would be more evil would be to give you temperature in degrees Celsius, milliliters here, and atmospheres in millimeters of mercury. So there could be additional unit conversions. It doesn't look like I've done that here. And
I mean, that's fine, but like, if you were to just like, okay, here's your limiting reactant problem plus find P on top of the limiting reactant problem. I mean, converting to liters and Celsius, that's not that difficult, but it just adds more math when you have to find,
right.
That's all.
No promises, Michael, but I don't think I do that.
Okay, good.
Yeah. Any other questions?
Professor, I have a quick question, and this might be a more a limiting reactant theoretical question.
Sure.
But that first part where you found out the moles of the H2 and that number of 0.161 moles, like, what does that tell us? That's how many moles of H2 we started off with?
Yes.
Okay. Okay, thank you.
Sure. Yeah, the analogy would be in previous limiting reactant problems, you'd find the moles of the reactants, but you'd be given grams. And so now that we have gases, we have to be given all this other information before we can find moles. Yeah. Any other questions?